Okay, related rates, taking the derivative with respect to time, taking the derivative with respect to time. T is time, the most ultimate independent variable, right? Time is independent of pretty much everything. It waits for no man. And unfortunately, it waits for no woman. Sorry, ladies. But find you a good man that will wait for you, right? Yeah, and listen to the Brad Paisley song, Waiting on a Woman. See, this is the stuff we need to have less and less of, I think, if we're going to stay on track. But it also is part of the fun of the class. Yeah. Okay. I would tell you this, and I'm recording this. So I had my summative with the principal on Friday during my conference, and we were talking about when he was in here. And there's like 5 levels, like level 1 through 5, right? And 3 is right down the middle. And he's a 3 guy. He had meetings. He says, I like to have a 3 in every classroom. And there's a lot of different things he measures you on. But if you're a 3 all the way down, you're a competent teacher, and you're going to do the kids right. He wants 3s, and he's very stingy with anything above 3. That's what he told me. And I can tell that, right? He has pretty high standards on the grading system. He gave us a 5, and I say us because it is y'all collectively with me. He gave us a 5 on classroom culture, and then a couple of other things as well. And not just 4s. He gave 5. He gave several 4s as well. I didn't get anything below a 3, but I got a lot of 4s. I got 2 5s. And he says, that's good. He said, you need to know how good that is, because he doesn't give out like rarely 5s, but he was impressed. He was impressed with y'all. So thank you. Yeah. And so anyway, we had a long conversation about, how other teachers can get to that level, and he wants to use me, but I don't know. A lot of it is just like my favorite quote by Vince Lombardi back there. If you're not fired with enthusiasm, you'll be fired with enthusiasm. Yeah. It's a great quote, right? You got to be fired up with enthusiasm. And if not, we will enthusiastically fire you, right? Get out of here. And enthusiasm is one of those things that you can manufacture. You can fake that until you make that. It becomes real, okay? I've given several speeches, and that equation over there is the X factor. Have I talked to you all about that equation? Yeah, the X factor is enthusiasm. So when I gave that speech at one of the NHS inductions, I saved that quote to the very end. And I said, here's a quote from my favorite football coach, Vince Lombardi. Then I stepped away and I put on an overcoat, and I got a little hat, and I put on some glasses, and I was trying to look like Vince Lombardi. And I stepped up from behind the podium and I said, grab, grab, grab. Nobody's tackling. And I did that without a microphone. And then I kind of stepped back behind the podium. I was like, oops, sorry, wrong Lombardi quote. And then I said that quote. So yeah, it served its purpose. Yeah. They chuckled. Yes, they chuckled enthusiastically. And those who didn't were asked to leave with enthusiasm. Yeah. All right. So let's jump to example 6. Okay. Example 5 is muy importante. So if you want to slow that one down, because it's one situation, and there's a lot of things that change. Okay. And then it's humor. This is always a humorous depiction of what's happening. So watch that. All right. Example 6. You did example 6. Okay, cool. So here we are. Example 7. 2 cars are riding. That should be driving, I guess, right? They're right. Or maybe they could be on the back of a truck or something, but they're each separately driving on 2 different roads that meet at a 90-degree angle. Car A is 3 miles south, traveling north at 40. Car B is 2 miles east, traveling east at 50. Oh, how fast is the distance between the 2 cars changing at this moment? Step 1, we got to read that and interpret it as a related rate problem. How do we know it's a related rate problem? What's that? There's a couple of things. Yeah, 2 cars are changing. It's asking about how fast something is changing. So, and then the other thing that we know it's related rates is because they're giving us rate of change per time. So it's per time. It should be per time. Feet per second, miles per hour, degrees Fahrenheit per day, whatever. All right. Now we typically, if you saw the video, even though there's time involved, we don't have the variable t in our equation most of the time. So most of the time we're taking the derivative implicitly. All right, so step 1 is just like it is in an optimization problem. We need to draw the scenario. So I'm going to let these 2 black lines be the 2 roads, okay? And there's the intersection at a 90-degree angle. All right. Car A is south of the intersection. So I'm going to come down here and I'm going to use maybe blue, and I'm going to call this car A. He's south of the intersection and he's traveling north. So he's heading this distance going up at 40 miles per hour. So this is important. If you're calling the distance that car A is from the intersection A itself, that would be beneficial. So don't really make a distinction between car A and the distance car A is from the intersection. So that's an unknown. That's changing, right? You have to label all your variables that change. If it's a constant, you don't have to label it as a variable. You can just call it that number. So now here's the important part. 40 miles per hour tells us how fast A is changing. So we always write that as d variable dt. So once we establish the position or the stagnant quantity as A, the change in that quantity in Leibniz notation is dA dt. And I'm going to label that as some type of 40. And here's the most important part. This is why it opened up with Mortimer's height changing. You're in charge of assigning a plus or minus to that. It's your burden's on you. Because if you're off by a negative in your calculations, sometimes you don't just get the opposite of the right answer. Sometimes you get a different number. So is that positive or negative, and how can we tell the rate? Why is it positive? It's going north. Now, normally that would be true. But A is measuring the distance the car is from the intersection. There you go. All you have to do is ask yourself, is A increasing or decreasing? If it's south traveling north towards the intersection, A is getting smaller. If A is the distance from the intersection, A is getting smaller and it's negative. And that's kind of an eye-opening thing, because most people want to say it's positive because it's going north. Well, if it were north of the intersection heading north, now A would be getting bigger. Super important. Okay, car B is 2 miles east. So I'm just going to draw this right here, purple car. It's 2 miles east. So I'm going to let B be the distance it is from the intersection. And at that moment, it's traveling east. So it's heading further away from the intersection at 50 miles per hour. So dB dt, the rate of change of B's distance, is what type of 50? Positive or negative? Positive. Now, you don't have to put a plus sign in front, but I am, just so I can see that I deliberately considered the sign. And that's because B is getting bigger. It's to the right of the intersection, heading to the right. All right. How fast is the distance between the two cars changing at this moment? So as the crow flies, as they say, let me label this on the other side. You can label this on the other side. Let's let that equal A. Now I'm going to draw a line from one car to the other. At that moment, and that's the other thing, at that moment, okay, instantaneously, how fast is that changing? I'm going to call that D for distance, big D, not little d, big D. So I'm looking for the rate of change of that distance with respect to time. That equals question mark. Okay. Now, are any of those variables, A, B, or D, constant throughout the life of this problem, or do they all change? Are they? D changes? Yeah, but A and B also change, right? A is getting smaller and B is getting bigger. The reason I bring that up is because in the previous ladder problem, you don't hear that very often, right? In the former ladder problem, LADDER, the length of the ladder was 10, and that was the hypotenuse, but we labeled it as 10. We didn't label it as L for ladder because the ladder didn't change, right? So there's no need to get that involved. But in this case, the hypotenuse does change as the two cars change. So this is important because it gives yourself a target. Now, the fun part that I like is identifying what I again call the snapshot moment. And you don't have to draw it in a camera, but I just like to. There's the flash bulb, old school camera. This is going to be what the values are at that moment. These are values that change throughout the life of the problem, but we took a picture. And what are the values of A and B at that moment? Well, it tells us that A is 3 miles south. So A is 3. We're not measuring, it's not -3. This is not a coordinate grid. It's just an aerial view. It's 3 miles south. And then B is 2 miles east. Okay. Now, it would be nice to know what D is at the moment, but let's say I don't need it. I can find it when I need it. But that right there is all just making sense of the information given. That's all that is. We haven't really done anything yet. Now we need to do something. Since d dt is our desired change in the rate, here's why it's called related rates. Before I can relate the quantities A, B, and D to each other, before I can relate their rates, I need to relate their quantities. Before I can relate the rate of change of A, B, and D to each other, I need to relate their quantities. So you just look at your picture here. A lot of times it's geometric. In a right triangle, how do I relate A, B to D? Pythagorean theorem. Okay, so here's your equation, right? A squared plus B squared equals D squared. And you're done. There is no necessary secondary equation. Now, sometimes there might be, but unlike the optimization where we're trying to get a single function as a function of a single variable, two variables at most, one on the left and then one on the right, we can have as many variables as we want to in here, as long as in the end we know the information. This is your quote unquote position function. Okay. What that means is if you know A and B at the moment, like we do, if we know where they are at that stagnant snapshot moment, I can find the D value, or vice versa. If I know B and D, I can find A. But now I want the rate equation. So here's the money step. I'm going to take the derivative now with respect to time of the whole thing. Okay. And here we go. Every variable A, B, and D is going to get a chain rule, d variable dt, because there's no t's in here, right? So the first one becomes 2a to the first times dA dt plus 2b to the first times dB dt. I'll stop after this derivative. And then that equals 2 big D dd dt. And that's why you want to use a different d. Wow. Right? It's just a power rule, but every single variable gets a d variable dt, right? Instead of 2a plus 2b equals 2d, we get that. So look at how many unknowns we have. 1, 2, 3, 4, 5, 6. There are 6 unknowns in this problem. If d dt is my target, right? That's the only one that I require then not to know. So I need to know a and b at the moment. Which do I? Yes. I need to know dA dt and dB dt at the moment. Do I? Yeah. And then I need to know d at the moment. Do I? No, but I can figure it out by plugging it back into the positive position function. Okay. So I'll stop right there. This is your velocity, quote unquote, velocity or rate equation. Okay. So that went by fast. We were having fun. Tomorrow I'll finish. I'll do this problem and then we'll look at cones. Cones are probably one of the most favorite shapes of College Board and for me. I use a cone every morning when I make my black silk coffee. Thank you all again, by the way, for Thursday's fantastic fanfare. It was fantastic. Had a great time. I appreciate y'all.